Do a little adjusting over here. There we go. Okay, so we are going to continue with chapter 8 today. We have about 10 slides-ish left to go. The test is Wednesday, so the test covers chapters 7 and 8. You have the study guide, so make sure you're using that study guide to help you narrow down what you're focusing on. There are, I think, only 3. Actually, I should open it up as I'm talking about it. There's not a whole lot of mechanisms. I was going to say, I think there's only 3 mechanisms from this chapter that are starred on the study guide, meaning those are the only ones that could be on the test, but I'm opening it up because I don't remember if 3 is correct and I don't want to lie. 1, 2, there's 4. There's 4 that are starred on the test. And so actually the one we're going to talk about right now is the last one that has a star on it on the study guide. And so we're going to talk about the last 4 reactions in the chapter and then look at some multi-step synthesis problems. So the test will have kind of a handful of multiple choice questions, which are really like concept questions. So if you have an SN1 reaction and you increase the concentration of the reagent, how will it change the reaction rate? Which of these solvents would be best for an E2 reaction? So kind of like the concept side of what we've done. There are nomenclature questions because we did alkenes and halogens. And then there are box questions where you're filling in the missing product or filling in the missing reagent. There are mechanism questions, and then there's multi-step synthesis questions. So it's essentially an overview of everything we've talked about. Any questions about the test at all? Okay. So let's look at reaction number 7 then. So reaction number 7 is called a halohydrin reaction. And this is going to be very similar to our last reaction. So let me go back just a couple slides right here. So we looked at halogenation, which was our alkene with a halogen, and we added that halogen to both of the vinylic carbons. In this one, we're starting with an alkene. We are reacting it with a halogen. And our halogen can be bromine or chlorine. And we're using water as a solvent here. And this could actually be water or an alcohol group. And what we make is called a halohydrin. And so it's called a halohydrin because one of the carbons gets a halogen and the other carbon is going to get an OH group, or it will get the alcohol group attached to it. So the alcohol without its hydrogen, so making an ether. So we make, let's see, I was trying to figure out where to write this. We're going to make a halohydrin. Oh, actually, I'm sorry. I'm going to erase that and relabel this. We're going to make a halohydrin. The minor product that I did not mean to label is both of the halogens together. So notice that that's actually the same product as reaction number 6. So that's really kind of a side product that we wouldn't necessarily want to have happen in this reaction. If we did this with an alcohol, so I'm going to react this with Br2 and CH3OH. So there's my alcohol. That's my solvent. There's my carbon chain. My regioselectivity for this reaction right here. The halogen's going to add to the less substituted carbon, and then the oxygen will add to the more substituted carbon. So I'm going to put my bromine right here on the less substituted, and then right here would be the OCH3. So it'll be the oxygen and then whatever R group, whatever carbon group is attached to it. Let's see, we've talked about regioselectivity. Down on the bottom here, it is showing more of the regioselectivity. So we have our less substituted carbon and our more substituted carbon. So the oxygen group goes to the more substituted side. The halogen, in this case, a chlorine, goes to the less substituted side. The stereochemistry of this reaction is that it is an anti-addition. So we looked at the mechanism for reaction number 6 last time. The mechanism for this one is very, very similar. So that's what we're going to look at right now, unless there's questions on just the reaction to start with. I need to pull up my chat window. There it is.
Wait, for the top reaction with the bromine, how come the left side's more substituted?
Let me get a color here. Okay, so what we're looking at are these two carbons. Those are the only two carbons that can react because they're the vinylic carbons. We're looking at how many carbons they are attached to. This one right here is only attached to one other carbon. This one is attached to 2 other carbons. So that's when we're talking about how substituted it is. We're looking at how many carbons it's bonded to. Does that make sense?
Yes, thank you.
Okay, you're welcome. Okay, let's look at the mechanism. So as I said, this one's going to look super similar to reaction number 6. So here's our reaction number 7 mechanism. The first step, in fact, is exactly the same. So we looked at this one last time. It's kind of a weird one, but we're starting at the pi bond, and that pi bond is doing a nucleophilic attack. And so we talked about this one because we talked about the electron cloud around that bromine and how it can be kind of pushed, squished to one side. And that bromine can be a little bit positive because of an instantaneous temporary dipole. So we do a nucleophilic attack. The other bromine's going to take off. So that bromine's a leaving group. Our first bromine, though, does still have a bunch of lone pairs on it, and it's still an electronegative atom. So it can also do a nucleophilic attack. So in those arrows at the bottom that are kind of look like they're going in a little bit of a cycle there, we're doing a nucleophilic attack on the bromine and a nucleophilic attack by the bromine. It's playing both roles in that reaction. So we create, this is our intermediate. That's our bromonium cyclic ion. It's not happy. Because it's a 3-atom ring, it's going to have angle strain. Let me erase my little bracket I made. So here's our water. And remember this, if we had an alcohol, we would just write it like this, and we would go from the oxygen. So whatever the R group is, whether it's a methyl or an ethyl, we would just go from the oxygen still. But we're going to go from that oxygen right onto the carbon. And remember, we're going to go to the more substituted carbon when we do this. Down here, the bottom part of this slide is telling us why we're going to the more substituted carbon. As that bond starts to form between the oxygen and the carbon, the bond between that carbon and that bromine start to break. So this arrow starts to happen right here. The carbon that's in the middle of that becomes what we call a becomes a pseudo carbocation. So really it just means it has a partial positive charge, but a pretty strong partial positive charge. And we know that when a carbocation has more substituents, it's going to be more stable. So we want to go to the more substituted carbon so that it has a more stable transition state. So this is our oxygen going to our more substituted carbon. This is the bad one on this side because we have a less substituted carbon, which means it's going to be a less stable transition state. So our oxygen attacks, does a nucleophilic attack. Our bromine is technically a leaving group there. And so then in our third step We just have to get rid of that extra hydrogen that's on our oxygen. So we're just using another water molecule. We're going to grab onto that hydrogen and then break the bond between the oxygen and the hydrogen, and then we get our final product. If we were doing this with an alcohol, at that step, let me show you what it would look like. We would have our oxygen bonded here, whatever carbon group, I'm just going to put a methyl there, but if it's an ethyl, a propyl, whatever it is, that would be attached there, and our hydrogen. So we would still use whatever that alcohol was, because that's also our solvent. So there's a lot of it floating around. We would use that alcohol to grab onto that hydrogen, and then that hydrogen oxygen bond breaks. So all that's changing is this hydrogen right here. If we were using an alcohol, that would be in whatever our R group is. So same thing right here. Questions about this one? Okay, then let's look at number 8. Reaction number 8. So reaction number 8 and number 9 are very similar to each other. They differ in their stereochemistry. So number 8 is called an antidihydroxylation. So anti is telling us about that stereochemistry. Oh, actually, we didn't talk about the anti on the last one. Let me go back a slide. This step right here is showing us how it's anti. The bromine is on the top, and then the oxygen is adding to the bottom. So the bromine added to the top of the molecule, the oxygen is adding to the bottom of the molecule. That's what makes it an anti addition. So that is stated right here, but just to point it out in the mechanism. Okay. So this one's also anti. So that means that the two things that are getting added are going to get added in the opposite ways. So we do often show that with a ring because it makes showing the stereochemistry nice and easy because nothing's rotating. Dihydroxylation means that we're going to add a OH group to each of our carbons, to each of our vinylic carbons. So we're starting with our alkene. Again, it doesn't have to be in a ring. The ring just helps us see that stereochemistry a little bit better. This is done in 2 steps. So this one is literally written out as 2 separate reactions. So I'm going to write it down here. Let's see. We'll just do a regular alkene down here. In the first step, we're going to use a peroxy acid. So this is kind of our generic way to write it. This is a peroxy acid. So we've talked about peroxides before. Peroxides are when we have that oxygen-oxygen single bond. And we know what carboxylic acids are. So this is essentially putting the two together. So a peroxy acid has to have this functional group. There's going to be something else attached right there. But we have to have that carbon-oxygen double bond and then 2 oxygens single bonded together with a hydrogen on the end. So it is really like kind of merging a carboxylic acid and a peroxide into one molecule. The picture that's over here, this is a super common one. Let's see if I can do that without crossing anything out. It is called MCPBA. It stands for meta-chloroperoxybenzoic acid. So the meta, I don't think we've talked about meta at all. I was trying to think if it's come up. The meta tells us the relationship in the positioning. So the fact that those are separated by 1 carbon, that's what makes it meta. Chloro, obviously there's a chlorine on that ring. We have the peroxy acid part and it's on a benzene ring. So that's where the name comes from. I point this out because on the arrow, you might see number 1, MCPBA. And you need to know that that is a peroxy acid. It might also say peroxy acid or have our generic abbreviation. When we add the peroxy acid, our intermediate in this reaction is this guy right here, an epoxide. An epoxide is a ring that is made up of 2 carbons and an oxygen. So that's an epoxide. We will have a chapter later on. I think it's at the end of this semester. I was trying to remember if it was the end of this semester or the start of next semester, but where we will actually learn about epoxide reactions. So we'll see this one again, where the goal is to make that epoxide. For this reaction, though, our goal is to make this dihydroxylation. So in step number 2, we're going to add acid and water. So H3O plus. And what we will make is a diol, so a dialcohol, where our stereochemistry is trans. So the alcohols are in opposite positions from each other. That's where the anti-addition comes in. It's called a diol. We haven't learned how to name alcohols yet, but alcohols always end in OL, ethanol, methanol, propanol. And so putting that di in front of it tells us that we've added 2 alcohols. Regiochemistry, they're only adding to the vinylic carbons. We don't need to talk about Markovnikov or anti-Markovnikov because it's the same thing going to each carbon. So it's an alcohol to each carbon. Stereochemistry, we know that it's anti-addition. We've talked about that. So we are going to look at a little bit of the mechanism on the next slide. I can't remember if it's all of it. Let's see. Oh, it is kind of all of it. So this one's not going to be on the test. So we're going to talk about it a little bit, but keep that in mind. It's not one of the starred ones. This right here is why it's not one of the starred ones, because that's just kind of a mess. But we're taking that peroxy acid. We're doing a whole bunch of cycles within that ring. So we're doing nucleophilic attacks and loss of a leaving group and some proton transfers all at once. This is the transition state. So remember, each of those dashed lines is representing a bond that's either forming or breaking. So there's a whole lot of stuff happening all at the same time, but we make our epoxide. The second half of the reaction looks very similar to reaction 6 and 7. We have that 3-atom ring, so we've seen it with the bromine and the chlorine already. And then our alcohol, or our water, our oxygen, is attacking one of the carbons. In that first step, we are doing a proton transfer. This is kind of similar to what we looked at in our substitution elimination chapter in chapter 6. We know that oxygens aren't good leaving groups. And so we are adding that extra hydrogen to it. We're protonating it to make it into a better leaving group, because this arrow right here is showing it being a leaving group. So we're essentially doing an SN2 reaction right there. We're doing a nucleophilic attack and then the loss of a leaving group. And then because our nucleophile was neutral, we just have to take off that extra hydrogen. But we had that epoxide on the top of the structure, and then our alcohol attacks from the bottom. So that's why we get that anti-addition. We get the one with a wedge, one pointing down with the dash to get that shape. Questions about this reaction at all? Okay. So I said that number 8 and number 9 are very similar. Number 9 is a syn dihydroxylation. So we're going to add 2 alcohols again, but we're going to do it in a syn addition. So they will both be on wedges or both be on dashes. So we're starting with our alkene. And again, it doesn't have to be a ring. We're only showing it in the ring so that it helps us see the stereochemistry a little bit better. Now there's 2 different sets of reagents that will do the same thing. The top one, we have KMNO4, which is potassium permanganate. With water hydroxide, and it needs to be under cold conditions. And we make a cis diol. So we would also make the enantiomer of this where they both have dashes. But in this case, because there aren't any other substituents on the ring, because we have that plane of symmetry, having them both with dashes or both with wedges would actually be the exact same structure. In the bottom one, we have OSO4, which is osmium tetraoxide. And NaHSO3, so sodium hydrogen sulfite, and water. There are variations to this. So you might actually see this as Na2SO3 instead. It will do the same thing. What else? There's another abbreviation. Oh, when we have the OSO4, it's paired up with NMO. Let me draw you NMO over here. NMO is N-methyl morpholine N oxide. Let me move my label. It looks like this. Let me get us a little corner over here. So it's a ring. There's a nitrogen and an oxygen in the ring, and then some stuff attached to the nitrogen. It's just one of the extra reagents that's necessary to go with it. There's one more option though. This is one of those reactions that's a little bit annoying because there's just so many ways to do it. So instead of using osmium with NMO, it could also be an alkyl peroxide, which would just mean that we have a carbon chain with 2 oxygens and a hydrogen. So a very common one is that, which is tert-butyl hydroperoxide. So lots of ways to do this one reaction, which I know is not helpful, but there's definitely some similarities here. And what they have in common is that there's a lot of metals in this reaction. So the potassium and the osmium, they both have 2 steps. They both have bases in that second step. So one of them is the conjugate base of a stronger acid. The other one is just a hydroxide. So there are some similarities that you can pick out. We aren't going to look at the mechanisms for either one of these because they are both metal-based reactions. They don't really fit in with the patterns that we've seen. We've kind of looked at 2 basic patterns in this chapter, and this definitely just doesn't fit with that. So this is really just a flashcard, remember the reagents kind of reaction. Questions about this reaction? Okay. We're going to fill in some reagents this time. So we normally do filling in the product. So I'm going to have us fill in reagents. So this is similar to how you would see it written on the test. You'll be given the starting material, our alkene, and you'll be given products. And then you have to know what the reagents are that we need to put into those boxes to make those reactions happen. So we're going to fill in the missing reagents. What are we going to put in box number 1? So if we want to add a chlorine to one of our carbons and an alcohol to the other, this falls into the first reaction we looked at today. So we would need Cl2 and water to be able to do that. And then the other two reactions, we have a cis diol, and I know it's cis because they're both on wedges. And then I have a trans diol. And again, I know that because one's on a dash and one's on a wedge. So what are we going to put in the box for our cis diol?
Potassium permanganate.
Good. So that's our first reagent, KMNO4. And then what's in our second step for that one?
Peroxy acid.
So this one doesn't have peroxy acid. It does have hydroxide. Water and
Gotcha.
be under cold conditions. So this was the last reaction we just talked about. And then what about our, oh, go ahead.
Sorry, quick question. Do we have to know like under cold conditions?
Yep, because that's part of it.
Okay, thank you.
What about that third box then? What if we want to make a trans diol? What are we going to use to do that?
Would it be OSO4?
So OSO4 also makes a cis diol. So we could have put that in box number 2. That would have also fit there.
Could it be acid and water?
We are going to use acid and water in the second step. So step number 2 will be H3O+. What are we going to put in step number 1 for that one though?
Peroxy?
Yeah, our peroxy acid. So I'm going to put MCPBA, mostly because it's just the shortest way to write out a peroxy acid. But yeah, and so that is reaction number 8. So you don't need to know the actual reaction numbers. I'm just putting them there so you can go back and use them for studying. But there we go. Questions about any of those 3? Okay, we have one reaction left. I think that this one is kind of the coolest. It might be the weirdest. It is called Ozonolysis. Might have the coolest name. Starting with an alkene. We're going to react it with ozone. So O3. And we're going to react it with DMS, which is dimethyl sulfoxide. So it is that. DMS is one that we will see show up occasionally. So if you are building a little glossary index, I would suggest adding this one to it. Okay. And then what we're going to make are 2 carbonyls. And our carbonyls here will either be aldehydes or ketones. And whether they are aldehydes or ketones is going to depend on how substituted the carbons are. So really what we're doing is we're taking our alkene bond and we're cutting it in half. And so this part right here, let's try that again. I'm going to go right through the middle, becomes this ketone. And this part right here becomes this aldehyde. And so the reason why the one I circled in orange is an aldehyde is because there's a hydrogen right there. So if our vinylic carbon has a hydrogen attached to it, then it will become an aldehyde. And if it has 2 carbons attached to it, then it will become a ketone. One more thing I got to mention here. For step number 2, you might also see it written as zinc with water. Our book likes to use that version as well. That looked like another Z. Let's try and make that look more like a 2. I'm not sure if that looks better or not, but that's an alternative for step number 2. So it could be DMS or it could be zinc with water. All right, we're gonna do, well, let's see, I have a practice one on here, but I think we're not gonna do this practice one. I think it's more than what we need, but I do wanna do a practice one. So let me add in a blank slide. Oh, I know what we should do. Okay, wait, we're gonna do 2. Sorry. Let me put this over on the side. Don't know why I'm doing it in the middle. Okay. We are going to fill in the products. So we're actually going to do the bottom one first, but the top one's going to be good practice as well. It's just a little bit trickier. So with ozone, we're just going to break this double bond. And then the way that I think about it is that really we're just going to put an oxygen right there and right there. And so when you redraw these, you can keep that same basic shape. So I have the left side and the right side. So if I redraw this, I can just redraw the left side just like that. And I can redraw the right side just like that. And I'm going to put a hydrogen in here, not required. But a lot of times when we draw aldehydes, we include that hydrogen. So really, we just took that double bond, we separated it, and we put an oxygen on each of the ends of that double bond. That's not really what the mechanism's doing, but it's an easy way to think about it. It helps you see what's going on. And the way that these are drawn is definitely not the prettiest way to draw either one of these structures, but it helps us see the shape from the starting point to the ending point. Okay, I just saw the question in the chat and I'm real sorry, but I don't know if this applies to what we're talking about right now. Is that applied to this reaction? The last one. So this one back here? Okay, so the question was, what does the vinylic carbon become? So let's see, I wanted to use a different color. These are our vinylic carbons. The vinylic carbons become carbonyl carbons. So a carbonyl is just a carbon-oxygen double bond. And then what's attached to it will turn it into an aldehyde or a ketone or a whole other list of things that we don't need for right now. But our vinylic carbons become carbonyl carbons. Sorry, I missed your question. Okay, so questions about that first example.
So the oxygen is just like the barrier between both of them, kind of. There's two separate.
Yeah, it's two separate
Structures.
molecules. So if we were to draw this out and make it a little bit more pretty, we could write it like this. 1, 2, 3. We would write it like that. We'd have our two molecules side by side.
Okay, got it. Thank you.
Any other questions on that first one? Okay, let's look at the one above it then. So we have an alkene. We're reacting it with ozone. We have all the right components. We're going to break that bond between our two vinylic carbons, but they're in a ring, so they're not really breaking away from each other. So I'm going to draw this two ways. We're going to kind of do what we did on the bottom one there. We're going to draw it one way where it's not very pretty, and then the other way. There's my carbon chain. All that I'm missing is that double bond that was right there. So we know that the double bond between the carbons is gone, but what we now have is a double bond to an oxygen for each of those carbons. So I left it in its ring shape to draw it that way, but I'm going to show you one other way to do this. And to do it the other way, I'm going to count my carbons. So I have a 6 carbon ring. We'll give that methyl on the end, carbon number 7. So I'm going to start by just drawing a 7 carbon chain. And then we fill in the missing pieces. So I know that carbon number 1 is going to have a double bond to an oxygen. I added the hydrogen on there because with aldehydes, we generally show that hydrogen. And then I know that carbon number 6 is going to have a double bond to an oxygen. So the blue structure and the green structure are exactly the same thing. We've just taken that blue structure and kind of unraveled it to show structure, to show the green structure. I'll even add in the numbers here so you can see where the pieces are coming from. If this was a test question, both of those answers would be correct. It's just kind of two different ways to draw the same thing though. Any questions about those?
So on the bottom one, we have to, the green wouldn't be okay, right? We have to rewrite it as the blue.
This one that's right here?
Yeah.
No, that'd be completely okay.
Oh, okay, perfect. Thank you.
You don't want them touching. So there's, I drew in my little blue squiggle there as we were talking about it. That part's not necessary. You can erase that. They can't be touching because they're not the same molecule. They're not bonded to each other. But yeah, you can definitely draw it like that. And it does help sometimes to see it drawn that way because we're just keeping the shape of the original molecule the same.
Okay, thank you.
You're welcome. Any other questions about these ones? Okay, that was actually our last reaction in this chapter. We're not done, but that was the last actual reaction. The last section in this chapter then is looking at synthesis. And so we're looking at two types. The first one is just a one-step synthesis, which is really what we've been doing in our practice problems. It's what our worksheet for chapter 7 and what worksheet for chapter 8 today will look like. It's, if you want to do this reaction, what reagents do you need? If you're given the reagents, what products will you make? So it's learning and memorizing all of those different reagents to do the change that is being shown. And so we've looked at really 3 categories of reactions: addition, substitution, and elimination. The idea here is when you are looking at a reaction, we have to be able to use the tools that we've learned to do these different steps. So the example that's shown here is if we are doing an elimination reaction, we can use that to move the position of a leaving group. So in the first example, here's our bromine, and in the end, our bromine is over there. And so we can do that by doing an elimination reaction. So we can use some base to do our elimination. And then by adding a bromine right here, we know we're going to do HBr. We know we want that bromine to add Markovnikov. We want the bromine to add to the more substituted side. If we did bromine with peroxide, the bromine would add right back to where we started with. So we could do what if we wanted to do the opposite? We wanted to go from there and we wanted to make that. So again, we could do the elimination. I'm gonna have to go this way with my elimination. So we could add some hydroxide to do that elimination. And then to do the addition of that bromine at the less substituted side, we can do our HBr with some peroxide. So that was our, I think it was reaction number 2. Let's see. Yeah, it was reaction number 2. That was our anti-Markovnikov addition. When we're doing these as multi-step syntheses, we generally write the reactions on the line to kind of together like that. If you're doing it for a test question, it's a really good idea to include all of those intermediate. So you would want to draw out the alkene, and really that's kind of a partial credit thing. So if your test question, let me do a little erasing here. If your test question looked like this and it said, propose a synthesis for the following transformation. So that just means, how can I go from this to this? You would want to show the in-between products. You would want to show, okay, I'm going to add base to make this, and then I'm going to add HBr and peroxide to make this. If you just put them on the arrow and they're completely okay, then you're fine, you'll get your points. But if you just put them on the arrow and you have an error somewhere in the middle, then it will be a lot harder for me to figure out what you were trying to do, and it will be a lot harder for me to give you partial credit, because I won't know if you had the right idea but the wrong reagents. So you'll be more likely to get partial credit if you show me your in-between structures. The one underneath is essentially the same idea, but we're starting with an alcohol. And we know that alcohols are not good leaving groups. So we would need to turn that into a good leaving group first. So I would want to react this with tosyl chloride and pyridine. And then we could do an elimination. Now notice that where that double bond is, that's the Hoffman product. It's the less substituted double bond. So I would want to use tert butoxide to force that to go to the less substituted side. And then in the last step, we want the alcohol to add anti-Markovnikov. We want it to add to the less substituted side. So we're using that regiochemistry to our advantage by picking which set of reagents will put our functional group in the right position. So this is our hydroboration reaction. So BH3 with THF and hydrogen peroxide with hydroxide. So this would be a 3-step reaction. We'd have to create a good leaving group, do the elimination, and then add in our alcohol in the right position. So we are going to practice a couple of these. Do I just have, oh, okay. Just want to see what I have. I have a couple of blank slides left. Okay. There we go. So the last slide was moving a functional group. So we moved the bromine to a different position. We moved the alcohol to a different position. The other thing that we could focus on is moving the position of the double bond. So our double bond is right here between carbons 2 and 3. But what if we wanted it over here between carbons 1 and 2? And so the way that we can approach that is, and actually let me write this out. I'm going to write it out so it looks like it would look on the test. It would look like that. You'd have the reactants, you would have the products. You wouldn't be given this in between stuff. We're given that now because we're looking at how to do this, but you would be given these two portions, the reactant and the product, and asked, how do I do this? The goal with a multi-step synthesis is always the least amount of steps possible, because time, money, every time we transfer something in a lab, some of it sticks to the glassware, so we lose a little bit of it. So that's the reality of it. We would want the least amount of steps. That makes it efficient. But on paper, it's not a big deal. We're learning the reactions. So if you do this and it takes you 8 steps, but you got there, and somebody else did it and they did it in 2 steps and they got there, you're both going to get full credit. That part is not going to come into play when I grade it. So something to keep in mind. So if you are studying together and you do it in slightly different ways, but you both get there, that's okay. And that's something you can learn from each other about the different pathways, especially as we move up in our chapters. There's going to be multiple ways to do the same thing. All right, so let's talk about how to do this one and how we would show our answer. So the question is in blue. I'm going to do my answer in green. So if I want to get my alkene on the other side, I know that I can get there if I can get my bromine in that middle position. So I want to make this so that I can do an elimination to get over there. So to do that, I'm going to add HBr and peroxide. I want my bromine to be on that less substituted carbon. And then to do an elimination, but making that Hoffman product, I'm going to use my tert butoxide. So playing with Zaitsev versus Hoffman, Markovnikov versus anti-Markovnikov can really help us direct where we get our products from. Okay, let's do a couple practice ones. Okay, so here's our 2 practice ones. Here is how I suggest you approach these. When we look at a multi-step synthesis, we want to see what changes are occurring. So first glance, with that first problem, we can see some stuff is different. We have a bromine on our reactant. We have an aldehyde on our product. We also want to count our carbons though. 5 carbon chain, and our bromine is on carbon number 2. In our product, we only have a 4 carbon chain. So we know that in this reaction, we're going to have to break off a carbon. Now, we actually only know one reaction that can break off a carbon. We also only know one reaction that can make a carbonyl. So knowing those 2 things can definitely help us figure out where this reaction needs to go. So one of the ways to approach this is by doing what's called a retrosynthesis. And a retrosynthesis is really just a fancy way to say, you can think about this from a backwards perspective. So if I have a 5 carbon chain and I want to go there, I can do that through ozonolysis. If I have a double bond, 1, 2, 3, 4, if I have a double bond between carbon 1 and this end carbon, and I do my ozonolysis reaction, that end carbon is going to break off. Now that end carbon, if we have a terminal double bond like that, that end carbon turns into CO2 gas and just bubbles away. So we don't catch it, we don't see it. So we lose a carbon when we do that reaction. So that blue part right there is technically what's called a retrosynthesis, because we thought about how to get to that product in reverse. We thought, well, if I can get an alkene in this position, then I can get to that carbonyl. Then we can say, well, I know how to get to that alkene from right here. I just need to do an elimination and force it to give us the Hofmann product. So that tert butoxide, again, comes in handy. We're going to get that double bond on that end position. So my answer, if this was a test question, everything that's in blue would be my answer. Questions about that one at all?
So what are you like technically like asking for in these type of questions? Like the intermediate part of what?
I am asking for the reagents. How do we turn this molecule into this molecule? What reagents need to be used? This alkene structure down here is not a required part of your answer, but if you have something a little bit wrong in your reagents, those intermediate products will show me your thought process, show me what you were trying to do, and it will help you get partial credit. So the other way we could have drawn this answer, let me put it in orange. I could have said, first I'm going to add tert butoxide, and then I'm going to add ozone, and then I'm going to add DMS. That would also be a completely correct answer, just putting all your reagents on the arrow step by step by step. You're not showing any of those intermediates though. So if you wrote DMP instead of DMS, well, okay, there's not a real whole lot of ways to interpret that. If you put a different base instead of tert butoxide, let's say you just put hydroxide, that's going to put your double bond in the wrong spot. But if you drew this to show me this is where I want my double bond to go, then you would get some extra credit points. I'm sorry, not extra credit points. That was the wrong phrase. You'd get some partial credit points. If you don't show me that, then I'm going to think, well, if they use just hydroxide, their double bond's going to go over there. That must be what they wanted because that's what they used and they didn't show me anything else. And so you wouldn't get as many partial credit points for that. So highly, highly suggest that you draw out all those intermediates. Questions on that one at all? Okay, let's look at one more. So on the last one, we have a ring that has an alcohol attached to it. And in the end, we still have a ring, but now we have two alcohols attached to it, and they are in a trans configuration. So again, we can kind of think about this from a retro perspective. How can we get two alcohols on a ring that are trans to each other? What reagents do we need to do that?
Would it be MCPBA?
It is MCPBA.
Would it also be H3O?
Exactly. And to do that, we need to start with an alkene. Do we know how to go from an alcohol directly to an alkene, or do we need to turn that into a two-step reaction? And really, actually, to be honest, both, you could say yes to both of those because there's more than one way to do this. So how can we go from an alcohol directly to that alkene if we wanted to do this in just one step? So we can use concentrated sulfuric acid. That will do our elimination reaction. So we talked about that at the end of chapter 6, but it was also at the beginning of this chapter when we were looking at the difference between addition and elimination. So I'm going to show you one other way to do this. I'm just going to change colors. We could also react this with HBr. That does our substitution. And then we could do some base to do our elimination. So both of those would be completely correct. You could also react it with the tosyl chloride to turn it into a better leaving group. So there's a handful of ways to do the same reaction. Some of the steps, like that last one with the MCPBA, there's only one way to do it. But other portions, you will have some options.
So like the answer for this question, like let's say on the test, would it just be MCPBA and H3O plus?
No, because to use MCPBA and H3O plus, you have to have an alkene. So that would only be half your reagents. So your full answer would have to be the acid with the MCPBA and H3O plus, or instead of the acid, you could use the HBr and the hydroxide, but you have to show the reagents you need to create that alkene. Because if you just add MCPBA and H3O plus to our alcohol structure, it's not going to react. We have to react it with that alkene.
Thank you.
You're welcome. Can you draw the tosyl chloride? Oh. Okay, can you draw the tosyl chloride option and what reagents? Yes. Okay, so question in the chat asked to draw the tosyl chloride option. So I'm going to do, let's see, I'm going to erase some of the stuff on the top here. I did have 2 blank slides. I don't know why I didn't use both of them. Okay, so if we did this, let's see, let me find, we'll do an orange here. So we're going to do this, I'm going to show one more answer for the same question. We're going to use tosyl chloride with pyridine. And we would make OTS. And then we can use some base. So I'm just going to use hydroxide, nothing, no need to get fancy. We'll get our alkene. And then we would use MCPBA with H3O plus. So if that were my answer, the orange pathway would be another alternative for this one. Questions about that one at all? Okay, let's do another one. So I was trying to open up our test so I can look to see how I wrote my other questions. Let's go do a little rearranging here of windows. There we go. Actually, I think the ones we've done are a pretty good representation of what's on the test, but let's do one more. Man, where'd the test go? There it is. Got hidden behind my Zoom window. Okay. Okay, so the way it's worded on the test, just so I'm showing you the same language, is provide a pathway of reagents to get from the given reactant to the given product. That's how it's worded on the test. Oh, I'm missing a carbon. There we go. All right, so first thing we're going to do is we're going to count carbons. We have 1, 2, 3, 4, 5, 6. We have a 6 carbon chain with a 7th carbon attached. 1, 2, 3, 4, 5, 6. We have a 6 carbon chain with a 7th carbon attached. That's good. We don't have very many reactions right now that will change the carbon structure. We really only have one. Ozonolysis will cut that double bond in half. So changing a carbon structure is going to be pretty rare. So we want to start by just double checking. Are we changing anything about the carbon structure? And we're not. What we see though is that in our reactant, we have a double bond between carbons 1 and 7. Now, how you number those does not matter. You're numbering them for yourself so that you can keep track of everybody. So I would suggest numbering the reactant and the product in the same way. But where you start, where you end, whether you use numbers or letters, does not matter. So I know that I have a double bond between carbon 1 and 7. Over here, my bond between carbon 1 and 7 is now a single bond, and carbon number 2 has an alcohol attached to it. So that's really just my little summary of how the reaction has changed, how we are going to change our reactant into our product. We're going to need to get rid of that double bond. We're going to need to get an alcohol attached to carbon number 2. Now, carbon number 2 in our reactant is not a reactive carbon. We can't just add an alcohol to carbon number 2 in the state that it's in. In order for us to add an alcohol to carbon number 2, we have to make that a reactive carbon. And when I say a reactive carbon, that means that it either needs to have a leaving group attached to it, or it needs to be part of an alkene. There are other things that will make that a reactive carbon, but we haven't learned what they are yet. So those are our only two options. We need a leaving group or we need an alkene. Now we could kind of analyze this a little bit further. Right now, in our reactant, carbon number 1 and carbon number 7 are the only carbons that we can do anything with. They're the only reactive carbons in our reaction. That's because they are the only ones that are part of a double bond, and there's no leaving groups in that structure. So we can do an addition reaction and add something to carbon 1 and carbon 7, and then use that to continue on. Any thoughts on what we should do?
Could we use water, like H2O?
In the very first step?
Yeah,
Here?
because an alkene and a water create an alcohol.
Yes, but we do need some acid in there too. So we need some water
right.
with some acid.
Water with acid.
Okay, so if we add water with acid, is my alcohol going to add to carbon 7 or carbon 1? Is this Markovnikov or anti-Markovnikov?
Markovnikov.
Okay, so there's my alcohol. So how are we going to get an alcohol on carbon number 2 instead of carbon number 1? What could we do next? So really, what can we do to get rid of that alcohol and make carbon number 2 a reactive carbon? Yeah, so someone put in the chat. Oh, wait, go ahead.
Oh, I was just gonna ask if you could add more water.
So adding more water is not going to really do anything to this one, because really water is our solvent. So there's kind of just water hanging out. So adding extra water won't help us out here. But in the chat, somebody suggested elimination. And so that's exactly the pathway we want to take here. So if we have an alcohol, we know that they're not good leading groups. So there's a couple ways to do this. The fastest way to do it, so the way with the least amount of steps, is concentrated acid, so concentrated sulfuric acid. There's our double bond. On the last slide, over here in the blue, green, and orange, we talked about a couple different ways to do that elimination. So all of those would have worked as well. So we have really one step left here. We want to add an alcohol to carbon number 2, but we want to add it. Do we want to add it Markovnikov or anti-Markovnikov?
It'd be anti.
Yeah, and we can even put those little notes in there for yourself, or even it can be on your test, it can be for me, so that you're telling me that you know what you're doing. Those things can help you get some partial credit if maybe your reagents aren't quite right. Do we remember what reagents we need to do to add an alcohol anti-Markovnikov? So this is our boron set of reagents. So BH3 with THF, and then in step number 2, we have hydroxide and hydrogen peroxide and water. And I believe, trying to remember where my answer key is. I think my answer key is digital. All of the multi-step synthesis on the test can be done in 3 steps. So this one would be considered 3 steps because we needed 3 arrows to get there. If you end up doing it in more than 3 steps, that's okay. Because like we talked about, this elimination down here could be done in 2 steps instead of 1. So having more is always okay. But I wrote them out so that they would all be 3 steps. Any questions on this last example?
Yeah, I'm confused as to like where you got the BH3 and the THF.
So this was reaction number 4 from this chapter. And it's an anti-Markovnikov addition of an alcohol. So it's just one of those sets of reagents you have to learn and remember.
Oh, okay. Thank you.
Any other questions on this one? Okay, that is all I got for you today. So we are ending a little bit early. Emma, did you have anything you wanted to say about SI at all?
Sure. I've been sending email reminders, but we did a chapter 7 cumulative review over the weekend. That went pretty good. And then tomorrow we're going to have chapter 8 review cumulative from 2 to 3:30, I think I scheduled it for. Justin also has his SI sessions. I think he's doing his a little bit earlier than mine, maybe like at noon. Also feel free to go to him. He's also a great resource. What else? It's going to be about an hour and a half review, but because I cut my SI hours short in the mornings, I always stay a little bit extra. So if anybody needs any help, I can stay like another half hour to help out any other question. And then Wednesday morning, we'll have our Q&A. So yeah.
Awesome. And if people can't show up at the beginning, like they, have another class or whatever, can they show up halfway through? Is that okay?
Yes, definitely. Yeah. And then I'm always available through email or text if anybody has any questions.
Awesome. Thank you. Any questions for Emma? Any SI questions? Okay, so I will hang out till the end of class. We are going to do worksheet 8 in lab today. I don't plan on taking all of the time so that you can use the extra time to study and ask me any questions you have. So we will specifically go over the questions that will help you prepare the most for the test. So the ones that are most similar to the test, and then some of the ones that might not quite match up as well, we might just kind of skip over those ones. So I will hang out and answer any questions you have, but that is all I got for you for today. So I will see you, what time? 10. I will see you at 10:15 in lab, but feel free to hang out for the next 15 minutes or so and ask me any questions you have.
Thank you.
Thank you.